In this video, we are going to look at the zeros of polynomials. So up here at the top, I said, or I typed, recall the zeros of a polynomial f of x are the solutions of the equation f of x equals 0. I have that as a recall because there is another video in our YouTube channel that discusses zeros of polynomials. It is the one about sketching polynomials. Also, in that video, it was discussed what multiplicity is. So you can kind of read through this yourself, but basically if we have a factor that appears more than once, then when we set that factor to 0, we would say that 0 has multiplicity, however many times that factor appears. So for example, if you had the polynomial function f of x equals x minus 3 times the quantity x minus 1 squared, the 0, 1 of 1 would have multiplicity 2. Lastly, here before we start some examples, we have this theorem. So this theorem on the exact number of zeros of a polynomial, if f of x is a polynomial of degree n greater than 0, and if a 0 of multiplicity m is counted m times, then f of x has precisely n zeros. Okay, what the heck does that mean? So let's jump in. So we have this polynomial function, f of x equals x times the quantity x plus 3 to the 5th times the quantity 3x minus 7 to the 4th. So to explain this theorem, I actually typed this into a math website and I asked it to expand. So if you were to multiply x times the quantity x plus 3, but I've got that 5 times. Okay, so 2, 3, 4, 5 times. And then multiply by 3x minus 7 4 times, since we have that exponent of 4. Okay, I'm running out of room now here. Okay, you get the idea. Okay, so I did not do this math myself, but I let a website do it, and this is what I got. Now, do we need to expand this? Heck no, we do not need to. I'm just trying to explain this theorem here. So what the theorem says is we look at the degree of the polynomial, and the degree is 10. So I'm expecting 10 zeros. Now, they don't have to be unique. It's not like I'm going to get 10 unique zeros, but I'm going to get 10 zeros. Okay, so I expanded it to try to explain to you what this theorem is saying. Okay, so I'm expecting 10 zeros. I'm also going to tell you here in a little bit how we could have found the degree without expanding. Okay, so I'll tell you a quick way here in just a second. This was also covered in the other video as well, but okay, so to find the zeros, I need to solve f of x equals 0. So this is going to give me the zeros of this polynomial function. So I'm going to set my factors to 0 to solve this equation. So this means that x equals 0, or x plus 3 equals 0, or 3x minus 7 equals 0. Now, I dropped the exponents because, as we see above here, if I'm raising x plus 3 to the 5th power, that's just 5 factors of x plus 3. And each of them are going to have the exact same solution. So I'm going to get x equals -3 no matter how many times I set x plus 3 to 0. So I only need to set it to 0 one time. And then over here, I'm going to get 3x equals 7. So x equals 7/3. So I'm getting 3 zeros. Okay, but up here, I was expecting 10. I technically do have 10 because this -3, it counts 5 times because the multiplicity of that 0 is a 5. And this 7/3, well, it counts 4 times because the multiplicity of it is a 4. So if you say that the 0 counts as 1, and then -3 counts 5 times, and then 7/3 counts 4 times, then technically you do have 10 zeros. They're just not 10 unique zeros. So my zeros are, so one of my zeros is 0, and its multiplicity is just a 1. It only counts one time because the exponent on that factor is just a 1. Then I have a 0 of -3, and its multiplicity is 5 because the exponent is a 5. And then finally, 7/3 is my last 0, and its multiplicity is 4. So by counting each 0 the same number of times as the multiplicity, technically we do have 10 zeros. Okay, now we're not going to make you do this, but I'm just trying to kind of prove a point here. So if you write out each 0 the same number of times as its multiplicity, you will see that we do technically have 10 zeros. Now, remember how earlier up here, I used a website to expand this, and I said, we won't never make you do that. But to get the degree of 10, you don't need a fancy website to expand this. You can just add the multiplicities together. Okay, so if we add these multiplicities, you get the degree of the polynomial function. So I could have, just added the exponents to get a degree of 10 instead of using my fancy website to expand that. Okay, let's see a couple more. I won't explain these in as much depth as I just explained that one. Okay, so to find the zeros, I need to solve the equation f of x equals 0. Now, in the last problem, it was already factored for us. F of x was factored. This one is not factored, so we're going to have to factor it ourselves. So I'm going to attempt to factor by grouping since I have 4 terms. So this is my first group here, and this is my second group. And I'm going to factor a GCF from each group. So the GCF of that first group would be x squared. So let me factor x squared from the first group. And I'm left with 5x plus 3. Now from group 2, their greatest common factor is 9. I am going to actually have to pull out a -9 though, because I want this binomial to be the same as this binomial. And so in order to be left with 5x plus 3, I have to factor out a -9. So taking a -9 from a -45x would give me a positive 5x. Taking a -9 from a -27 is going to leave me with positive 3. These match, that's awesome. I need those two to match, otherwise factoring by grouping fails. So my factors are 5x plus 3 and x squared minus 9. However, hopefully you recognize x squared minus 9 as a difference of squares. It will factor further as x minus 3, x plus 3. So looking at this original polynomial function, I'm expecting 3 zeros. And this time I'm actually going to get 3 unique zeros, because by setting each of these factors to 0 and solving, I'm going to get 3 answers to this equation. So one of my zeros is negative 3/5. I'm just solving this. I'm subtracting 3 from both sides and dividing by 5. This gives me 3, and this would give me negative 3. So I have 3 zeros, and they all have multiplicity 1. And I can see that because each factor just appears one time. So all have multiplicity 1. So this is a 0 with multiplicity 1. This is a 0 with multiplicity 1. And this is a 0 with multiplicity 1. Okay, last one here. So in order to find the zeros, I need to set f of x to 0. And this is another one where we need to factor ourselves. It is not factored for us. So first thing I notice is there is a GCF of x cubed. So let me factor that out first. And then after factoring this GCF, I'm left with a trinomial. To factor the trinomial, I'm going to need to use the AC method. Okay, so let me kind of step aside here. Let me do it in a different color. So I'm not going to forget about that x cubed. I'm just going to try to factor this over here, and then we'll go back to this equation here. So for the AC method, I take a times c, 9 times 49. And 9 times 49 is 441. So I'm going to look for two numbers. I want them to add to 42, and I want them to multiply to 441. Those two numbers are, I know these are kind of some big numbers here, but it's 21 and 21. So I'm actually realizing now that this is a perfect square trinomial. So we'll see what that means in terms of factoring here in a second, but I'm just going to continue with the AC method. So the AC method, I replace my 42x in the middle with a 21x plus 21x. And then I factor by grouping, just as I did in the previous one we factored by grouping, previous question. So in group 1, I have a GCF of 3x, and I'm left then with 3x plus 7. In group 2, I have a GCF of 7, and then I'm left with 3x plus 7. So my two factors are 3x plus 7 and 3x plus 7. That's what I mean by this being a perfect square trinomial. When I factor it, its factors are the same. Okay, so back over here, so I'm going to kind of section that off. So back over here, solving f of x equals 0. Don't forget about your x to the third. So I've still got an x to the third. And, you know, instead of writing 3x plus 7 times the quantity 3x plus 7, I'm going to go ahead and write that as 3x plus 7 quantity squared. So looking at the polynomial function, I'm expecting 5 zeros. Now, I don't have 5 unique zeros, but technically I do have 5 zeros. So one of my zeros is 0 because I have this factor of x that counts 3 times, by the way. So one of my zeros is 0 with a multiplicity of 3. My other 0 is negative 7/3. And its multiplicity is 2. So I only have 2 unique zeros. They are 0 and negative 7/3. But if I count each the same number of times as the multiplicity, I do technically have 5 zeros. So my 5 zeros are 0, 0, 0, negative 7/3, and negative 7/3. Okay, but we only have to write, you know, the 2 unique ones and then just, you know, we're going to mention multiplicity. Okay, that is the end of this video. Thanks for watching.